So this is an interesting paper that takes a slightly different approach to this idea of why we had such record warm temperatures over 2023, 2024. I've discussed this already a little bit. We said it was much higher than what we would expect just from the combination of background global warming that's been going on, plus the El Nino, which is a mini global warming because it releases the heat stored in the ocean into the atmosphere and temporarily spikes the global mean temperatures. And there are other papers which have argued that maybe the underwater volcano in 2022 contributed by throwing up water vapor, maybe wildfires contributed greenhouse gases, maybe cleaner air increased the absorbed solar radiation, and there is even one paper arguing that cloud covers changed in such a way that albedo was reduced, so that also led to more energy absorption and so on. But then the question is, it was, the warming was high, we were caught by surprise, so it may have been unlikely, but is it really unexpected in the sense that is the system able to produce such jumps without any prediction or predictability? So internal variability is what we call them, like El Nino is an internal variability, but then there's another paper that tried to do the forecast prediction of whether 2024 would be warmer as well than 2023, and they initialized the forecast on July 2024 and claimed to have made a prediction that they 20 July to or November to December or some period of 2024 would continue to be warmer, and their argument was that there was an ENSO independent warming in the northern hemisphere, which is internal variability. Internal variability basically means it's not predictable. It's like random noise, whereas the signal is either the El Nino, which has a predictability of over 6 to 12 months, or global warming, because you are increasing greenhouse gases, and you can say how much warming will occur if you know how much the greenhouse gases are going to increase and so on. So this model takes a different approach. It says that models do produce such warmings purely from internal variability, so it's not unexpected. It was unlikely because we didn't predict it and we didn't expect it, but we should have expected it, maybe, right? Global ocean surface temperatures were at record levels for more than a year from April 2023 onwards, exceeding the previous record in 2025-2016 by 0.25 degrees C on average between April 23 and March 24. The nearly global extent and unprecedented intensity of this event prompted questions about how exceptional it was and whether climate models can represent such record-shattering jumps in surface ocean temperatures. Here we construct the observation-based synthetic time series to show that a jump in global sea surface temperatures that breaks the previous record by at least 0.25 degrees C is a 1 in 512 year event under the current long-term warming trend, 1 in 205 year to 1 in 1185 year event with 95% confidence interval. Basically, if you know time series and you know the warmings, you can statistically estimate the return period of these jumps in warming in the record that you have. And notice that they are here focusing on sea surface temperatures, not global mean surface temperatures, which are slightly different. Land has many patterns of warming and cooling as well, and ocean does too. So the global mean sea surface temperature and global mean surface temperature are not necessarily exactly the same. Without a global warming trend, such an event would have been practically impossible. Using 270 simulations from a wide range of fully coupled climate models, we show that these models successfully simulate such record-shattering jumps in global ocean surface temperatures, underpinning the model's usefulness in understanding the characteristics, drivers, and consequences of such events. These model simulations suggest that the record-shattering jump in surface ocean temperatures in 2023 and 2024 was an extreme event after which surface ocean temperatures are expected to revert to the expected long-term warming trend. So it's a spike and it will come back, but as of now we are sitting and watching a pattern that is called a La Nina, even though it's very unusual compared to traditional La Ninas. So we'll see more about whether the ocean was really taking up heat like a La Nina year does or not, and whether that was also responsible for this continued warming into 2024. Okay. So let's read a little bit, because most of the idea is already in the abstract, that models do have these jumps in them purely from internal variability. So if 2023, 2024 happened, we didn't predict it, it doesn't mean that they are really not predictable, but it's a tricky issue, because even if you predicted the global mean, can you predict the global pattern? Because the local impacts, all global warming is local, as I always say, and local impacts are going to remain on local changes in temperature or temperature gradients and so on. Although record-breaking jumps in global SST occur when a long-term warming trend is superimposed onto an exceptionally warm year owing to climate variability such as El Nino, the record-shattering jump in globally average SST from April 2023 to March 2024 has broken previous records by a substantially larger margin than previously record-breaking jumps in SSTs. The three largest margins by which globally averaged SST previously broke records were 0.16 degrees C in 2015-16 and El Nino, 0.14 degrees C in 97-98, another El Nino strongest of the 20th century, and 0.09 degrees C in 2009 and 10, which was not a strong El Nino, but there was an El Nino. Owing to the unprecedented margin in the record-breaking jump in SST in 2023-2024, which is at what did we say it was? Yeah, let's keep going. I keep forgetting the numbers I just read. Okay. Owing to the unprecedented margin in the record-breaking jump in SST in 2023-2024, this jump in SST came as a surprise for the public and the scientific community. This event has raised questions about the likelihood of such a jump and whether jumps of this size are simulated in climate models. The failure of state-of-the-art climate models to reproduce events such as the jump in SSTs in 2023-2024 would consequently question the ability of these models to assess future risks associated with anthropogenic climate change. However, if climate models are able to simulate such record-shattering jumps in globally average SSTs, they would deliver analogs to study the evolution of the ongoing event and to see whether temperatures decrease again or remain high. So even if you didn't predict it, you still want to see where it is going now after 24 has come to an end. I'm recording this in 25. Where are we going now? Will it continue to be warm, or are we going to come back to the original level of warming rate that has been happening in the background? In addition, the climate models could be used to identify the drivers of such record-shattering jumps in SSTs and their consequences for other parts of the climate system and the marine ecosystem. Okay, it's basically saying models are not that bad, don't worry about it. Return period of record-shattering SST jumps. Then here we use observation-based monthly mean SST estimates from various data and reanalysis products and extended reconstructed sea surface temperatures to quantify the likelihood of the global SST jump in 2023-24 and assess whether it could have occurred without anthropogenic warming. So to the extent that the emissions have continued to rise, could we have expected this? Or could this happen even though we didn't expect it, let's say? Okay, so owing to the relatively short observational SST record, return periods of rare events such as the record-shattering jump in globally average SSTs observed in 2023-2024, they keep repeating this phrase for some reason, cannot be directly inferred from that observational record. To quantify the likelihood of a record-shattering jump in globally average SSTs that exceeded the last record by at least 0.25 2.25 degrees C as in 2023-2024, we constructed synthetic time series of 100 million years using an autoregressive model of order 1 using observation-based estimates of the trend, autocorrelation and standard deviation of the annual globally averaged SSTs with respect to uncertainties. So it's a statistical methods where you produce trends using the data that exist by using these autoregressive approaches. Based on these synthetic observation-based time series, the record-shattering global jump in 2023-2024 was a 1 in 512 year event. That's the mean estimate under the current long-term warming trend, which itself is 1 in 205 year to 1 in 1185 year event, as we said before, and those are statistically significant as well. This result is qualitatively insensitive to the choice of the autoregressive model to the methods that are used to estimate the trend, the correlation and the standard deviation of annual globally average SSTs, as well as to the observation-based SST dataset that is used for the analysis. So it's a robust result. Without the underlying warming, a record-shattering jump as observed in 2023-2024 is practically impossible. In other words, that kind of a jump riding on a background warming is going to give us this kind of a jump, and not without the background warming rate. We found indeed no record-shattering jumps in our synthetic time series without a long-term warming trend, irrespective of the variability or autocorrelation characteristics. Okay, it's a statistical way of saying that this warming is a big jump, but given the background warming, it shouldn't have been unexpected. Record-shattering SST jumps in climate models, then, having quantified an observation-based estimate of the return period of such record-shattering jumps in globally average SSTs, we show that such jumps exceeding the previous record by at least 0.25 degrees C were simulated 11 times across 270 simulations from 35 different state-of-the-art climate models between 2000 and 2040. These 4 decades encompass the time when the record-shattering SST jump occurred in the real world. So we'll look at the figure in a minute. As the 270 climate model simulations here comprise a total of 11,070 years, the likelihood for a single year to experience a record-shattering global mean jump in SSTs as observed in 2023-24 in the climate models is 0.1%, making the record-shattering SST event in 2023-24 a 1 in 1006 year event in climate models, which is 1 in 563 years to 1 in 2016 year event, and that's a statistically significant result. Okay, so basically the models have a certain return period for such jumps of this magnitude, and observation-based estimates say it was once in 585 years or whatever. Although the return period estimate based on climate models is approximately twice as large as the observation-based estimates of the return period, it lies within the confidence interval of the observation-based estimate, and the confidence intervals of both estimates largely overlap. The difference in the return period might be owing to lower warming trends and higher autocorrelations in the models compared with the observation-based estimates. However, the observation-based estimate of the return period is also highly uncertain, as it is difficult to estimate the trend, variability and autocorrelations over a short time series that is strongly influenced by natural climate variability, so that the return period of such events might well be 1006 years as estimated from the models. In other words, there are uncertainties in both observational estimates, and models are of course not perfect. So to look at it in a more specific pictorial way, record-shattering jumps in global SST as observed in 2023-24 also occur in climate model simulations. So here we have 1990 to 2019 period in the gray lines, 2020 in the blue line, and 2021 in the the orange line here, this is from CMIP6 CAN ESM5, a particular experiment of the CMIP6 suite of models. If you just look at observations, here you are with 1993 to 2022 and 2023 in the blue line, and 2024, which started out warm and then has dropped off since the summer, and this is presumably because we flipped into a La Nina, even though I keep insisting that the pattern is quite different. And this is another model with ensemble members, so different period, and basically arguing that models do produce such jumps. Okay, these are model estimates, here are the observational estimates. You can see the 23-24 jumps as opposed to the previous period is quite significant, and models can do that as well, even though they are not 2 years in a row. So here 2003 was still it was higher, 2004 was also higher, so it is 2 years. Here also 2 years in CMIP6 model. This is a CSM model, also has 2 years. So basically arguing that models have also produced such jumps in their simulations, so internal variability can produce such jumps. So probability density function, looking at return periods, then it peaks around here, I don't know, we can read mean is 512 years with long tail, the median is 448 year here, and this is the 95th percentile confidence, and we are all within that. So the return period of record shattering jumps in annually averaged global SSTs based on past observed SSTs, observation-based estimate of the probability density of the return period of record-shattering jumps in synthetic time series of global SSTs that break the previous record by at least 0.25 degrees C, the mean return period dashed back line and the median return period and the limits of the 95% confidence interval are shown. You get the idea. Okay, so here is some more detail. Margin of record breaking SST events delta SST. So average delta SST over 60 south, 60 north. You have to be careful, the poles are not included here, especially since the Arctic has polar amplification going on. Various things included. 2023 is up here, and various other years are identified, different models. So 30 GFDL ESM2 members, various years showing jumps, 50 CSM2 large ensemble members, and NOAA OI SST. Okay, I won't read the details, but you get the idea. Record breaking SST events between 2000 and 2040 between 2000 and 2040 in the models, so return period in years. Okay, the return periods are important because can the system really generate big events very often, or do they remain such rare events? And if they are rare events, are they let's say it happens, then two things we need to understand: will it continue at that warming, or will it come back? And what are the events that are potentially associated with such jumps? 2023, 2024 were full of extremes around the world, wildfires, floods, droughts, etc. Can we then also produce the impacts of such jumps? That's the main goal in the end. Okay, that's why I'm going to just be brief here again. NOAA OISST for 23-24 had basically warm everywhere except here. The El Nino obviously shows up very strongly. CMIP 5 simulations 2020-2021, you can see that looks maybe somewhat similar, even though stronger here. GFDL ESM2M, it's a model, large ensemble. Number 27 shows some similarity, and this is for 2016-17 from the large ensemble of CSM. Okay, so anomalies of record-shattering jumps in SSTs in observations and climate models are mostly localized in the equatorial Pacific, North Pacific, and North Atlantic. So Northern Hemisphere seems to be favored in all these jumps that are produced in the models, and The 2024 forecast experiment also, I am not reporting that paper, but that paper also argued that the 2023-24 El Nino contributed, but then there was a warming in the northern hemisphere, which is seen here. There is also land warming, but this paper focuses only on SSTs. That warming is ENSO independent, so it's some sort of an internal variability, and this seems to indicate that such jumps in the models are always associated with excess warming in the northern hemisphere, even though the warming hole here shows up as well in this simulation for 2016-17, which was also an El Nino. So the models do not when in the CMIP6 simulations, they are long simulations starting sometimes from pre-industrial revolution going into the 21st century. So they don't reproduce necessarily internal variability like an El Nino in 97-98 or 2015-16 or 23-24, but they reproduce the trend over these times given the greenhouse gas emissions, volcanic forcing, land use change, and so on and so forth. So where are we going with this then? SST evolution after record-shattering jumps. We now use these model simulations to understand how SST anomalies typically develop over the years that follow a record-shattering jump in SSTs. To the extent that models are producing these jumps in their runs, what happens in the models after the jump occurs? In all simulations, the global SST anomalies stop being record-breaking, that is, they fall below the previously measured temperatures in the same month between May and October of the second year of the record SST anomalies, that is 13 to 18 months after the beginning of the jump in globally averaged SSTs. In the real world, global SSTs dropped below the record levels in July 2024, 15 months after the beginning of the record-shattering jump in global averaged SSTs. Furthermore, SST anomalies in climate models return to their level before the jump between September in the year after the jump in SSTs started and September in the following year in 8 of the 11 simulated jumps. However, in 3 of the 11 events, the SST anomalies do not return to the pre-jump levels over the next 10 years and beyond, so that the global SSTs have indeed permanently risen to a higher level in these simulations. However, even in these 3 cases, SSTs revert back to the expected long-term warming trend over the course of at most 8 years and do not shift to a new higher or steeper warming trajectory. The 3 cases occur in some models that are doing something. 2 climate models with extremely high transient climate responses outside the recently assessed range and with atmospheric warming rates from 1981 to 2014 that substantially exceed the observation rate. So models are not all the same. Their sensitivity to increasing CO2 are different. That's what we call transient climate response. This is all a bit tricky. You have to know the details, but nonetheless, these are the best tools we have, so we keep squeezing them to understand as best as we can where we are going after this record warming. As atmospheric warming and sea surface warming are generally strongly linked, the overly high SST warming rates facilitate continuing high levels of SST anomalies after the record-shattering jump in SSTs. Okay, so essentially we expect that we will stop warming and the record-shattering jump should end by September 2025. If, however, observed SSTs do not return to pre-jump levels by September 2025, we expect SSTs to revert back towards the long-term trend within a few years. If this were not the case, the ongoing extreme events would not be consistent with climate model simulations. In other words, we have reached a no analog state somehow in 2023-2024, so we sit and watch how we are doing. Outlook on warming rate and climate models then, based on long synthetic time series with temporal characteristics that match the available observations, we estimated that the observed record-shattering jump in globally averaged SSTs in 23-24 was a 1 in a 512-year extreme event. So 1 in 205 year to 1 in 1185 year event. based on current warming rates. Such a jump would not have been possible without anthropogenic warming, which means anything you add in terms of internal variability is based on the background warming. If you didn't have the background warming, you wouldn't get a jump from one year to the next of such a big magnitude. That's the main point. We have further shown that climate models indeed simulate such global annual record-shattering jumps in SSTs that exceed the previous record by at least 0.25 degrees C, but global mean here means 60 south, 60 north. Okay. Moreover, the estimated return period of these events in climate models, 1 in 1,006 year events in the model, is within the confidence interval of the observation-based estimate of the return period. Furthermore, in these models, the simulated SST anomalies drop below record levels between May and September in the year after the jump in SST had occurred. So 2023 was warm. What we are looking for is 2 years jumping together, 2023-24, and models do produce such 2-year jumps, and then the idea is what happens after that, and we said it does come back. If not in the following years, then it will happen in a few years after the jumps. On the basis of the simulated record-shattering jumps, we conclude that it is likely that SSTs will return to pre-jump levels before September 2025. In the few simulations that do not simulate a return to pre-jump levels, SSTs revert to the expected warming trajectory over the following years. Sorry. Thus, SSTs have not shifted to a higher or accelerated warming trajectory after a record-shattering jump in the models. The ability of climate models to simulate both the magnitude of the SST jump and the timing of the decline of positive SST anomalies enhances confidence in their use for future studies to understand the length, intensity, and drivers of such extreme events, and to quantify their impact on regional weather systems and their potentially devastating consequences for terrestrial and marine ecosystems and their services. Well, the idea that we didn't actually expect or predict and have had a hard time explaining says that internal variabilities do surprise us, and then the predictions, it's argued now that the predictions, seasonal predictions, actually show the impact of the biases in the model trends. You think the models are initialized and then integrated forward for a short time, so the long-term trends don't have an impact, but unfortunately it turns out that there is a fingerprint of the trends or the biases in the trends on the seasonal forecasts, which makes the challenge much harder in terms of being able to estimate the impacts of the jumps on regional patterns and impacts. And that's the ultimate challenge in terms of providing early warnings for adaptation and managing extremes and so on and so forth. So the problem is hardly completely understood or answered, but at least we know that models have the internal variabilities in them that produce such jumps with some return periods which are in the same range as observationally estimated return periods. That's the best we can take out of this at this time. Okay, see you in the next topic, which is also related to 2023-24, but in the context of marine heat waves.